thank you very much. Hi, everyone. It's nice to be here. So first of all, big thanks for the invitation to this track, to Valerie and Maria-Nick. I'm Christopher Irrgang. I work at Robert Koch Institute in Germany. Robert Koch Institute is Germany's national public health institute. And yeah, like in many other countries, there are now the topic of AI is going through the ceiling. And there's now a new center for artificial intelligence and public health research, which is basically one of the departments of Robert Koch Institute. And yeah, you can see it here. So it has got its own building, and we are located in the uppermost floor there. And this department has 4 units, and I'm leading the one which works on the intersection on public health, climate, and artificial intelligence. And yeah, climate analytics for current and future health threats is kind of the overarching topic that I will talk about. And yeah, last year we saw that climate change made it again to the news very often. So with record-setting temperatures in July, NASA said something like that July clocked in as the hottest month on the record ever since the late 1800s. July broke multiple global temperature records, and we had probably one of the hottest days on Earth. So to put this a bit into perspective, of course, this is not the first year where where Earth was under heat stress. But when we look into the global temperature records over many years, and here we look into the records over the last 2,000 years, we see that over the last 200 years there was this really unprecedented warmth and unprecedented rise of temperatures caused by anthropogenic greenhouse gas emissions, or in other words, by us, actually. And when you elongate this curve further back into the past, this just continues. And it's more or less safe to say nowadays that the generation that lives today experiences temperatures like a modern civilization has never before in the last couple of thousands of years. And of course, this has not only impacts on Earth and on the biology and on the ecology, but also on us humans, on our society, and on our health in a warming world. And this already has been acknowledged also by the IPCC. Climate change and health is a topic now as well there. And I took one of the figures from the latest assessment reports just as an overview, which shows the heat humidity risk to human health in the future. So now we are not looking into the past, but what might going to happen. And we see a couple of plots with different scenario temperatures. So in the middle, we see in the left-hand side, we see warmth up to 2.3 degrees, then up to 3.1 degrees, and up to 5.4 degrees. And related to these temperature increases that we might expect in the future, we see which parts of the world might be under particular heat stress and health stress than in terms of heat-related mortality, for instance. Now, this is a very vague overview, of course. And the more you zoom into specific regions, a whole range of different factors becomes important all of a sudden. So it could be socioeconomic factors, how people live, local factors in the health systems, and you can probably name a couple of dozens more. At the moment, we are more or less on track of the middle panel. So also not only the region close to the equator are under heat stress in the future, and of course also today, but we can also expect that heat stress will expand to the more temperate regions, especially also to Europe. So now we zoom in fact, to Germany and look more a bit into the topic of heat and mortality and climate impacts. There has been there's a lot of research on this already ongoing over the last years, and you can see a figure here that shows for the years from 1992 to 2021, I believe here, heat-related deaths in Germany, which are estimates based on all-cause mortality and temperature records that we have. And this study caused a lot of impact also in the media and in the news, because the estimates have been that in the 3 very hot summers in Germany, 2018 to 2020, there were more than 90,000 deaths related to heat in Germany. And the way you do it is that people try to calculate excess mortality. So we don't really actually know how many people really died of heat in Germany, but this is an association based on the temperature and based on the excess mortality that we can see during the summer months. And these kind of studies are currently conducted in many countries because this is, of course, not only a problem that we see in Germany, but in many other countries all over the world. Heat is becoming more and more a burden on health. And as a result of this research, we now have, since the last year, weekly reports on heat-related mortality at Robert Koch Institute, which is in essence a website where numbers are published, where people can track and inform themselves about the situation on current heat impacts, and also how the scientific community is dealing with this kind of topics and how they produce the results that they see. So this is definitely an important milestone for outreach and communication here. But so far, we have only seen, in terms of heat-related mortality, this kind of bar plots and this kind of time series analysis. So this leaves a lot of information and discussion, of course, out of the room. And this is where we set in now with artificial intelligence. And we asked ourselves, if we know, of course, or more or less in terms of time and in terms of total estimates how many heat-related deaths there are in a country, we are, of course, then interested if we could perhaps also do a spatial analysis and see where in Germany are the high-risk regions, where are the temperatures particularly extreme and related to local heat-related mortality, what is the impact of urban infrastructures, for instance, and so on and so forth. And these kind of studies are very difficult for many reasons that we are going to talk about a bit now. And yeah, for those of you who are interested in these kind of things, there is also a paper attached to it, a preprint at the moment. You can have a look at it. We also not only publish the research, but also the methods that we develop. And we hope that also other countries or other health authorities might adopt these kind of approaches to see if they can plug in the numbers they have from their countries and see if they can run similar analysis and get also perhaps similar insights than what we have here. So we already heard in the entry talk a lot about challenges with AI and data in terms of the many different categories, and I will talk a bit about two important data challenges that we see when we run these topics. And this is not only related to AI and heat-related mortality, but also when we try to combine climate data with other health data, for instance, the spread of infectious disease, which is another topic we are working on, or infodemics, which is another topic that we heard a bit about in the earlier sessions on AI and public health. So what kind of data would we need if we work on like the spatial risk for heat-related mortality? There is, of course, weather and climate data. So this is the prerequisite that we need. And since some time now, we have very high-resolution data available for many years. And these data look like the maps that you see here. So for the whole country, we have data on a 1 by 1 kilometer grid for daily values. So we have one map for each day with min, with max, and with average values for the last 20 years. So this is really good data, really high quality data, and this is one source that we are going to make use of. Then we also use climate projections from the IPCC because we are, of course, not only interested to look into the past and into the present, how the situation is like at the moment, but we would like to make estimates on how the situation is likely going to change in the future under climate change and under perhaps different pathways that might become possible in the future. Then we need to use mortality data, and here we use all-cause mortality data, which is in essence time series data. So there's different data sources available on daily and weekly counts, on different demographic categories, and also on different spatial scales. And this is really important to note here, that some data is available on national scale, so we have time series for the entire country. Some data is available on a state level, where we have something for the different Bundesländer in Germany. And then in addition, we also need to have data on the current demographics in Germany. In particular population statistics, which are curves that you, I guess, also familiar with, how the population in our country structures in terms of age, in terms of other categories. And that also is available, again, on different spatial scales, so perhaps on the state level or on the county level. So we are not really talking about multimodality here. We are not really talking about multimodality here, but even the integration of the different data types is already quite a challenge, because we don't really have a process equation, for instance, that links climate data or weather data with population statistics. So we need to come up with methods that can make meaningful sense by integrating this kind of different data scales, data types. And second is the topic of data scales, which is another challenge that we work with. So as I mentioned in the beginning, temperature data we have on a very high resolution, so 1 degree by 1 degree. And all this other data is aggregated over different administrative levels. So some might be on this county level, which we have 400 in Germany. Some might be on the state level, which we have 16 in Germany. And some data might be available only for the entire country. And this data fragmentation, if you want, in terms of spatial scales, is also the reason why many studies work on aggregated data for an entire country. Because, and of course I'm a bit paraphrasing here, spatial aggregation is always the easy kind of direction. You can always say, okay, I use all the data that I have on the different kind of scales, I bring it to a common denominator, use everything on a scale that is included in all of the data, and perform my analysis there. But of course you lose a lot of information that you have in some of the data at least, and that you of course don't want to throw away and still somehow make use of. Going the other way, trying to get a consistent picture on the highest resolution possible, that's the difficult part. And that is where we try to adopt an AI mechanism and build a technique that tries to combine and solve these two different kind of challenges. So how does that work? This is kind of a scheme of the study that we have performed here. So we use a neural network, and the neural network is fed with these high-resolution temperature data that we have available. And what we try to predict, our target values, what should come out of the network, is a function that provides us the effect of temperature on mortality. And this function is unknown, and this is what we want to learn based on the data that we want to have. So this is not just a machine learning approach where we say, okay, we put something in, we get something out and be done with it. We still need to integrate it with our demographics and our mortality estimates. So in essence, this is more like a hybrid approach, because the target of our neural networks, or the output of the neural network, is then inserted into a population model from which we estimate death cases. And this is again the function here. This F is what we get out of the model. So then with this population kind of model that is fused with the neural network output, we try to predict and try to estimate the all-cause mortality, so everything that's included, all of the causes and dynamics, and try to recover the death cases that we have records of over the last 10 years here in this case. So all of the dynamics, all of the variation is learned by our network and inserted into this equation here, while population statistics, demographics, something like baseline mortality is something that we use as an additional input of this equation. And the network is actually fairly simple. It is not a simple feed-forward network as the scheme suggests here. It is a shallow neural network, but it has a couple of different interesting perks to it that makes it really powerful. And the first one is that it has a very dynamic loss function that works on different scales, and it tries to incorporate all of the different data scales that I showed you before, so especially the different kind of administrative level data that we have, and tries to incorporate these kind of scales while making predictions on the highest available administrative level. And the other important thing, which is not really visualized here, but it's still included here, is that this network also includes an attention mechanism that you also, I guess all of you are aware of, or at least the ones who work with machine learning from transformer-based models. And this combination is actually very powerful, even though the model itself is really simple. And again, there are a couple of more technical details, let's say, which are part of the paper. And if you're interested in that part, have a look at it. So what do we get then in the end? How does it look like? These are outcomes of the study, so the spatial risk analysis of heat-related mortality. And we see two rows. In the upper row, we see aggregated number of hot days. So this is something that we just analyzed. We see over the different 400 counties in Germany, the aggregated number of hot days. So the darker the region, the more reddish, and the more darker, the more hot days were there in the different summer seasons. And in the lower part, you see what our model produces in the end, which is the estimated risk of heat-related mortality on a regional scale at the same level where we also have the temperature data available. And these figures were simply not possible before with classical statistics and classical methods that have been used at our institute. And for reference, what you see here in blue is a map that shows urban agglomeration areas, so where people live in Germany, where are the densest populations, regions, and combining what we see here with the temperature maps from above, we see that the high-risk regions in Germany can be, or are mostly driven by two things. First, of course, by the heat. Regions that are exceptionally hot also lead to a higher heat-related mortality. This is, of course, what you would expect. And the other thing is that we see that regions where a lot of people live, so in urban agglomerations like Berlin, or also the Ruhrgebiet, which is a part of Western Germany, is a high-risk region because there is an additional temperature effect which is called like the urban heat island dome effect, which becomes present here then in the data as well, and basically falls out of this model. So now knowing this, again, I said earlier that we also want to look a bit into the future and try to assess what we might expect in the future in terms of heat-related mortality. And then we can use the model as we have it and try to not use past temperature data, but future temperature data. And there we use climate scenarios from the IPCC. And these are these SSP scenarios. SSP stands for Shared Socioeconomic Pathways. These are model simulations for different potential possible futures, let's say. They are categorized in different sectors, let's say. So SSP1 is something like a sustainability scenario where we conduct a sustainable transformation in our society, lower our greenhouse gas emissions, so on and so forth. And it goes all the way through a spectrum until scenarios that are still mostly fossil fueled, conservative thinking, directing, and also some scenarios which are somewhere in between. The scenarios relate to an expected global warming until 2100. And we pick 3 scenarios with 1.8 degree global warming, 2.7 degree global warming, and 3.6 degree global warming. We again use this data then for Germany, and that's what we see here. So this is the expected temperature increase for the different scenarios until the year 2100. And on the right-hand side, we see the related expected heat-related mortality in regard to these shared socioeconomic pathways. And it is somewhat summarized here in the top. 2 things I would like to highlight. The first one is on the current trajectory that we have at the moment, which is an expected global warming between 2.7 and perhaps 3 degree global warming. We see a risk factor of 2.5 for the heat-related deaths in Germany. So all the numbers that we have seen over the past 10 years on average there might be a need to multiply them by 2.5 to account for the additional heat stress that we could expect. Of course, this does not include heat-related adaptation plans because they are not included into these IPCC models and also not into our model. But it is definitely then, it already underlines the need that we should implement these, especially on a local level. But the much more positive news from this study is that actually if we constrain global greenhouse gas emissions and also constrain the impacts in Germany, we see that the heat-related mortality risk is automatically constrained then. So reaching climate goals directly supports our public health systems, and I think that this is really a positive news, and this is also really nice that we can quantify this in a way that it falls out of our study here. So yeah, I would like to end with this, with the positive news actually, which is I think something that should be done from time to time. And perhaps as the last thing, a little bit of advertisement. We are currently again recruiting at our center. Over the last year, we have been recruiting all the time. We are growing and are now something between 30 and 40 scientists on the PhD and postdoc level, and we are now recruiting for our third PhD cohort. We have 7 positions open at the moment with new projects related to vaccine-preventable diseases in Germany, AMR, but also more machine learning heavy projects on NLP, large language models. We heard a bit about that already, and also image data, for instance, unsupervised pattern identification. And yeah, if that's interesting for you or for people that you might know, spread the word. We are looking forward to it. And then I would like to thank you for your attention.